blocked me on Facebook, and now you're going to die. Shit!
Hello and welcome to the encryption module of the Practical Cryptography course. In this module, we'll discuss 4 different lessons. Those lessons are symmetric encryption, asymmetric encryption, hybrid encryption, and message signing. For each of these concepts, we're going to be providing 2 different examples. The first will be a very simple, high-level example to give you a brief overview of the concepts. The second will be slightly more realistic, show you how things work in real life. And before we get into each of those lessons, I do want to provide an overview of encryption. Encryption is the process used to provide confidentiality. If you recall from the first video in this series, confidentiality is the service that makes sure that only the intended recipient can interpret data being sent across a wire. Here's how that would work. Encryption would take data and turn it into something unrecognizable to anybody else except the intended recipients on the wire. The data before it's encrypted is referred to as plain text. It's also sometimes referred to as clear text. The data after encryption is referred to as ciphertext. The process of encryption turns plain text into ciphertext. The ciphertext should be completely unrecognizable and indistinguishable from random data on the wire. The reverse of the process is known as decryption. Decryption will turn ciphertext back into its original plain text. The idea is only the intended recipient should have the ability to properly decrypt the ciphertext. Now let's take this example a little bit further. Let's say this blue user is encrypting the word hello to this green user over here. Some of you may have recognized the transformation I used is referred to as pig Latin. One way or another, it's something that only the green user can understand. Now let's also say this blue user wants to send the word hello to 3 other users. Well, the blue user can't simply reuse the transformation they used before, because then the green user will be able to see and interpret all the data sent to the other users. We won't have confidentiality of these messages right here to these other users. Instead, for each new user that the blue user wants to speak to, the blue user needs to find a unique transformation to create unique ciphertext for each of those users. This way, the green user can't interpret what is being sent to the other users, or vice versa. The problem with this is that it doesn't scale. Creating these transformations is not trivial. Actual encryption algorithms require mathematicians and cryptographers to work together for years in big organizations to create industry-approved vetted algorithms. So trusting a random user on the internet to create a transformation that is secure is not a winning strategy. Moreover, it's very, very difficult to do these securely. At best, when you're doing just a simple transformation like this, you can really only consider that as obfuscation and not true encryption. Instead, the industry uses what's known as key-based encryption. Key-based encryption combines a standard algorithm with a secret key. Here's how that would work. Again, we'll have the blue user trying to speak to these 2 users, and here are the messages that the blue user is trying to send to the users on the right. What the blue user can use is a standard, industry-approved, vetted algorithm, and the blue user can reuse this algorithm with as many users as he needs. Then the blue user just needs to generate a unique set of keys for every single conversation they're going to have. This industry-approved algorithm, combined with 2 different keys, is going to create 2 different ciphertexts, which means the purple user won't be able to have any insight into the ciphertext sent to the orange user, and the orange user won't have any insight into the ciphertext sent by the purple user. The only way to decrypt this ciphertext back into this plaintext would be to use this set of keys. As long as the blue and the purple user have done a good job protecting these keys, anything encrypted with this key will have confidentiality assured. Now these keys are nothing more than a random set of binary digits. This is an example of a 10-bit key. The idea is creating the algorithm is very, very difficult, so you leave that to the experts to create industry-approved algorithms. You, as a user who wants to use encryption to provide confidentiality, all you have to do then is randomly generate a set of bits to use for each new conversation you want to have. That's the idea behind key-based encryption. In total, there are 2 ways to combine an industry-approved algorithm with secret keys. Those 2 ways are going to be the subjects of the next 2 lessons in our series. Those 2 ways are symmetric encryption and asymmetric encryption. The high-level difference between the two is that symmetric encryption is going to encrypt and decrypt data using the same set of keys, and asymmetric encryption is going to encrypt and decrypt data using a different set of keys. We will explore both of these in great detail in the next 2 lessons. In this lesson, we learn that encryption converts plaintext into ciphertext, and decryption is the opposite process, which converts ciphertext back into plaintext. Moreover, we learn that only the intended recipient should have the necessary keys to perform.
You blocked me on Facebook, and now you're going to die.
Shit!